Okay, so let's say if we have, let's say a farmer. Oh, there you go. Plans to fence a rectangular pasture adjacent to a river. The pasture must contain, I know it's one of the more popular ones, 180,000 square meters in order to provide enough grass for the herd. Okay, what dimensions would require the least amount of fencing? If no fence is needed along the river. Okay, so if we do a quick picture, just kind of describing it, let's say this is the river, and you're going to put a fence around there. And the area in here has to equal 180,000. So we make this X, and these two sides Y. Questions like this show up so many different ways, but they all kind of say the same thing. All right, so first we want to start with what's given to us. Yep, that's our area. Our area is 180,000. Okay. So we know the area is length times width. So we know our X times Y is 180,000. Uh-oh. And that's assuming your area is your X times Y. Okay. So we're actually looking for the maximum, or what's that? The least amount of fencing, so the minimum amount of fencing. So that's what we're actually looking for. So it's our, I guess you could say surface area, since it's not the perimeter, because we're missing that side there. So we can't say perimeter. Okay, so if we're looking for our primary equation, and that's our surface area is equal to, say, X plus 2Y. Okay, and that's assuming S is the length of the fence.
Why couldn't we say perimeter for that again?
Oh, because the perimeter is the length of all four sides.
Oh.
Yep, so since we're missing that one side, we can't really say perimeter.
You can't say like X divided by 2 plus Y or something like that, or?
There's two Y's, and that's why.
Or X
They're
divided
both
by
the
2
same.
plus Y, I meant thought.
X divided by 2 plus
The
y.
parameter is 2x plus 2y. That's a parameter.
Oh, yeah,
So
you're
you're minusing 1x.
yep, so you're kind of missing
Yep, okay.
one of the
It's
x's.
same thing, same formula, you're just minusing 2.
Gotcha.
Yep. So here we want this as one independent variable. And again, we have two. We have an x and we have a y. Okay. But up here, if you remember, you can make y equals 180,000 over x. Just divide both sides by x. Okay, so that means, is that the second or third step? I always forget my steps. I just kind of go with it. So I think that's the, yep, that was the third step. All right, so that means S can equal x plus 2 times 180,000 over x. Okay, where x is our independent variable. Okay, so that means if we wanted to simplify that, that would be x plus 360,000 over x. Okay, and of course our x is our independent variable. Okay, so now we want to find our maximum and minimum value, which means we have to find where the first derivative is equal to 0. And that's the fourth step. Nope, fourth step is the domain. Okay, so our domain, we know that x and y is greater than 0, so like I said, we don't really always have to put the fourth step, but I'll do it anyway. So x is greater than 0, and y is greater than 0. All right, so that means your fifth step, the rate of change of s with respect to x. Turn that this way. There we go. Okay, so that just becomes 1. And this, if you bring the 360,000 forward, yep, plus 360,000 times the derivative. Instead of x, we can make that x to the negative 1. Okay, so that's going to equal 1 plus, bring down our negative 1, so that makes that minus, and we subtract 1, so that makes that to the negative 2 power. So 360,000 times x to the negative 2. So our change in s with respect to x is equal to 1 minus 360,000 over x squared. Okay, so we just need to know where that is equal to 0 because that's our critical point. And I'll leave that up and we'll continue that on the next page. Alright, so we continue this. Let me actually write down where we left off. 1 minus 360,000 over x squared. So we actually want to know where that is equal to 0. Okay, so 1 minus 360,000, clean that up a little bit, over x squared equals 0. So if we add this to both sides, 1 equals 360,000 over x squared. Yep, so if you multiply by x squared, x squared equals 360,000. Then square root both sides. Yep, x would equal plus or minus 600, but we know that it has to be greater than 0, so we can just drop the minus 600. Okay. And if we actually calculated the second derivative, we'll see that it was greater than 0, so it's concave up, so we know that this will be the minimum. All right. So we know that's our critical point. Okay. You know, this is just a little extra. Verify that. The second derivative of s squared equal to, actually that's 720,000 over x squared. That should be x to the x cubed. Is greater than 0. Nope, that's second derivative. Oh, wait a minute. That's the first derivative. Yep, that would be second derivative. Greater than 0 when x equals 600. Like I said, we don't have to know the actual value, but we just kind of did that anyway. So we know it's local minimum. Like I said, it was an unnecessary step, but we did it just to practice.
Why was it local minimum? Sorry.
Oh, because remember that when you have the graph and your slope is increasing, that's your second derivative. So whenever it's increasing, your slope where it's equal to 0 is your minimum. Yep, so we know that since our acceleration is increasing, so our slope is increasing as it's going, it's greater than 0. So that's plus if you plug in 600, it's positive, so we know that it's going to be a minimum.
So because it's positive when you plug it in.
Yep. So we don't need to know the value, we just need to know whether it's positive or negative. Okay.
For some reason, I was thinking that was positive, it was maximum.
And that's one of those tricky parts of it, that with the second derivative, when it's greater than 0, you would think maximum, but it's actually the minimum.
Okay, so the first derivative, if it's positive, it's.
If it's first derivative, if it's going from positive and then negative, it's the maximum. But if it's going from negative to positive, it's the minimum. I know those little details are just brutal. All right, so we know that's our critical point, so we know that's our minimum. So S is a minimum. Remember, that's the length of the fence you'll need when x is equal to 600. And if we plug it in, since we know that, where's I? S equals x plus 2y. So if we go ahead and solve for, what was it? Do we have a y value? Nope. Oh, that's the minimum.
Why we have y over x?
Where's our y?
180,000 divided by x.
Yep, 180,000 divided by x, yep. There we go. So 180,000 divided by 600 gives us 300. I'm jumping ahead. Okay, so we know that x is equal to 600 meters and y is equal to 300 meters. That would be the least amount of fencing needed. which would be 300, nope, plus 2 times 300, which is 1,200 total meters. All right, any questions on that one? All right.
We'll have to do homework.
Hmm?
So we'll have to do homework.
Yep, I'm still writing. I'll leave that up for a few more seconds. All right, so let's say here we have a car rental company. Charges its customers P dollars. We don't know how many it is. We just know it's some value P. Let me clean that up a little. To rent a car. Well, a day to rent a car. Okay, where we know that P is anywhere from $45 to $200. Okay, now the number of cars rented every day, excuse me, can actually be written as the formula, can be modeled by the linear function. Uh-oh. N of P is equal to 800 minus 4P. Okay, so how much should the company charge to maximize their revenue? You know, just the fact that it says linear function, we can't use the second derivative test. All right, so for our first step, we have to look at what we're given. Well, we're given that the model for the number of cars rented is 800 minus 4P. Okay, but that's not our primary equation. Okay, we're looking at how much we should get to maximize our revenue. Now, revenue is how much you charge times how many cars you rented. So how much money you're bringing in. Okay, so our primary equation since we know that revenue is equal to the number of cars rented times the price of the rental. Okay, so remember, your primary equation is always going to be what you're trying to minimize or maximize. Okay, so since you're trying to maximize your revenue, that's going to be your primary equation. Okay, so we can just reduce that to R equals N times P. Okay. But we already know that N is equal to 800 minus 4P. So we can make that into an equation with one independent variable. Okay. So our third step, R equals N times P, since we know since N is equal to 800 minus 4P, we can make R equal to 800 minus 4P times P. Or we can make it 800P minus 4P squared, or we can flip it around. Negative 4P squared minus or plus 800P. Okay. Where in this case, P is our independent variable. Now, the fourth step is your domain, which they actually gave to you. That's your domain right there. Okay, so you know P is between 45 and 200. Okay, so to find our maximum value, we have to find out where our first derivative is equal to 0. But we also have to find out where our endpoints are, because they could be our maximums also. So we have to find all of them. Oops, so our fifth that would be determine your maximum. That's R prime of P equals 0 for your critical point.